Okay, so this page of the package. We're going to talk about, you know, those cell potentials that are all in your data booklet, all those numbers we've been using to figure out the voltage. We need to talk about where those numbers came from. Okay, so just like we did for electronegativity, we talked about how it was an arbitrary scale from 0 to 7, or 4, and somebody decided, hey, fluorine most, therefore it's 4, and everything else was sort of judged accordingly, right? So the same sort of thing here. The first thing I need to redefine for you, hopefully it's is the standard condition. That's that little knot that we see on all of these E values. So if you look in your data booklet, you'll see that each, at the heading, it's got that same little knot, I think it's a theta sign, as the delta H had in our first unit, right? And it still means standard conditions. So a reminder of what standard conditions is: 1 atmosphere of pressure, which is 101.3 kilopascals, 1.0 moles per liter, and 25 degrees Celsius. In Chem 20, this is SATP, as in standard ambient temperature and pressure, ambient being a classroom, a laboratory. So where these experiments are happening, it's the standardized temperature and pressure of that room. Everybody okay with that? So that we can compare our results here to somebody's results in Germany, to somebody's results in Russia, to somebody's results in China. That they all will have the same results, whether they're at sea level or at the mountaintops. You can still compare the results. Okay, so that's the first bit of understanding. The second bit is the actual number bit. So where do they get the negative 3.34 or the positive 0.76? And it comes from that each half cell, do you know what I mean when I say half cell? So if you had the two things and the salt bridge, right? I'm talking about half of it. So the one solution, let's call that zinc 2+, and the one metal, let's call that zinc. So we've got a zinc half cell here. You okay with that? And I'm just going to delete the other half of your experiment that you would have had in this lab. And we're going to reconnect, so take the salt bridge out. We're going to reconnect that half cell to this half cell. And this half cell is hydrogen half cell. Everybody has their data booklets open or one near them? Have a look at the voltage of the hydrogen half cell. So this wire I'm going to connect here. And I'll need a salt bridge from there to there. What is the voltage of the hydrogen half cell? Oh, look at that. So they called this 0 volts. 0.00 volts. And when they connect this system up to a voltmeter, what's the voltage on your zinc in your data booklet? 0.76? Yeah. Positive or negative? Negative. Okay. So when they hook this up to the hydrogen half cell, and if you notice, it's got a platinum rod because it needs to be inert. I can't have, like, the hydrogen half cell has to have an electrode, and I'm going to pick an inert electrode. And it's in H plus gas. Why H plus gas? Well, because on that little thing with the hydrogen, the other side is an H plus. So I want an H plus H2 combination, and the H plus is going to make my H2 bubbles there and some platinum. This is exactly what you made yesterday, right? You had H plus in your solution, and you didn't have platinum, you had carbon. And we need to collect the gas though. So this is just a gas chamber that helps collect the gas here, so that we can keep it at STP. Everybody okay with that? And when they set this up to the voltmeter, did you not use zinc yesterday? Right? Yeah. You used zinc yesterday, did you not? So you made this yesterday. And your voltage was supposed to be, and for some of you it successfully was, 0.76 volts. Everybody okay with that? What is voltage? What does this mean? Standard potential voltage. The amount of energy you get from the reaction. Okay. What did you answer in your sheets yesterday?
The difference.
The difference of?
Half half cell?
The half cells. The subtraction, the difference, the height of the waterfall. Right? So how high that waterfall is going to be 0.76. All right, so they decided to make hydrogen 0. They decided to read the voltage. And whatever they read on the voltage became the other guy's number. Does that make sense? And so then in the data booklet, they wrote zinc and zinc 2 plus, half reaction, and made that number negative 0.76. And what if they hooked up a iron 2? Fe and Fe2 plus. What would the voltmeter have said on that experiment?
Negative 0.45.
Negative 0.45 volts. And so therefore they wrote the iron 2 plus half reaction, Fe2 plus 2 electrons goes to Fe, and beside that they wrote 0.45 volts. Everybody get that? And the reason they could do this is because it doesn't matter. If you understand that these are just numbers, and the distance between this number and this number will always be the same. Why are you smiling?
Because I realized that I was in Bethan's lunch, so I have been eating someone else's strawberries. That's why.
Okay.
Okay, cool. This could not have gone anywhere. I really hope it's Kirsten's.
Well, it could be the grade 10s were in here this morning as well.
Yeah, I bet you read a note say sorry.
Sorry, I didn't know your strawberries.
Oh god. Good.
Note to yourself, don't
Yeah.
leave your lunch around Sarah. Okay. Okay, so what if I hooked up the zinc and the iron together? What voltage should I get? The difference. And so, tappity tap on your calculator, 0.76 negative, 0.45. The difference between those two numbers is 0.31. Agreed? Yeah. And so it doesn't matter if the chemistry team that did this for their data booklet at the very beginning decided to make that, let's make this 0.50. Okay? Then this, when I hook that up and I hook something else up, this would, negative, let's say, and then this would have to be negative 0.81. What's the difference between now these new arbitrary green numbers? If the scientists decided to choose this for the iron and that for the zinc, instead of the red for the iron and the red for the zinc. It's the same difference, because it's the same height of the waterfall. So if you hold your fingers like this, and you take a ruler, I don't have a ruler right in front of me because the Chem 20s have been stealing that. Oh, look. Okay, so if you hold a ruler and you hold your fingers exactly 2 inches apart, those 2 inches will be the same regardless of where the numbers are on this number line. Did you get that? So they decided to make hydrogen 0, and then from 0, where's 0 on this ruler? From 0 to 3 is still going to be a difference of 3. But let's say they decided not to make hydrogen 0. And this is where the tricky part comes in, and these are the kind of questions they ask. The voltage doesn't matter because electric potential is always a subtraction. So even if the numbers were all voltage higher, the subtraction would still be the same. So let's say on your data booklets, they decided not to make hydrogen 0, but instead they made, can I just have a quick look at your data booklet? What if they made the H2O2? What is H2O2 at the moment?
0.7.
0.70?
Yeah.
So what if they decided, it's very messy, what if they decided to make this number 0? So what's this saying? Well, here's my number line. There's a 0 here. But instead, I'm going to shift the 0 up here. What would hydrogen's new number be? Negative 0.70. Because the distance between them is still the same. What would zinc's new number be? So zinc was 0.76. What would zinc's new number be? I actually have to subtract it. No, wait. Hold on. Yes, I have to subtract it. Okay, I have to subtract it. So this makes this negative negative 1.46. So this is how you do it. For those of you that don't like the number line shifting thing, this is how you do it. Ask yourself, what did I have to do to the hydrogen peroxide to make it 0? Oh, I had to subtract 0.7. So I'm going to do that to all the others. I'm going to subtract 0.7. Kind of get it? Okay, Amanda, let's try a question. Okay? So go to the next page in your booklets. Okay. Assume that the reference half cell is changed to a standard mercury 2 half cell. So assume that we don't have hydrogen as my standard 0 anymore. But rather, I have the mercury 2 as my 0. Everybody get it? What is mercury 2 at the moment in your data booklet? Yeah, mercury is Hg.
Positive 25.
You sure that's mercury by itself?
Yeah.
Going to mercury 2 plus, not some other unusual ion. We're good, right? So it's mercury 2 is 0.58. What do we have to do to that number to make it become 0? We have to subtract 0.85 to make it become 0.00 volts. All right? So I'm going to do that. Basically what that means is I had to take my ruler and shift it down 0.87 spots. So as I shift the ruler down 0.87 spots, everything else is shifted down 0.87 spots. So what would the reduction potential, oh, there's something else I need to teach you. What would so notice the title of this chart is?
Standard cells and potentials.
The reduction half reactions electrical potential. Okay, so the reduction potential that's your data booklet, because they're all reduction reactions. Everybody okay with that? All right, so what's the reduction potential of a standard chlorine half cell if I've changed my standard cell to be the mercury 2? What is the current chlorine? The current chlorine?
1.6.
1.36 volts. And how I've shifted my ruler down 0.85. So therefore, I need to shift this down 0.85. And so my answer ends up being, oh, my mental math is too tired this morning. 0.51? Thank you. That's the new voltage that would be on our new data booklet if they decided to make mercury 2 the standard half cell. Everybody get what they're asking? Okay, try the next one on your own. Yeah? So it currently is this. What did I do to make the mercury become 0? I subtracted 0.85, so I'm going to subtract 0.85 from this because I'm moving the ruler down by 0.85. In fact, actually I'm moving it up. Anyway. And so therefore I get negative 1.11 volts. Everybody okay with that? Could you write the half reaction of the nickel? Could you write the reduction potential standard nickel-nickel half cell reaction? Well, you would go nickel 2 plus 2 electrons goes to nickel, and the voltage that for that, the standard voltage potential for that would be negative 1.11 volts. If they asked you to write the whole thing out. Everybody okay with that? Yes? What is the net cell potential of a standard chlorine nickel cell? So this is saying I'm now hooking up nickel and chlorine and a salt bridge. We wouldn't really be able to do this because chlorine's a gas, but anyway, pretend this is a sealed container, salt bridge somehow. You get it what I'm saying, right? What would the voltage be on that voltmeter?
Could you figure out the cell
6.
first and then subtract the...
You have to find like cathode and subtract
Just the difference between the two.
and then
Just the difference between the two.
Yeah, so, but you figure out, like, the cell, the whole entire cell of the chlorine nickel, and subtract that 0.85, is that what you did?
So there's two ways of doing it. Because of course it's still saying the mercury 2 half cell is now the reference cell, right? So let's take our answer to A and our answer to B and let's subtract them. Oh, which one's going to be the cathode? Without even thinking about it.
The chlorine.
CO.
Why?
It's positive.
Because it's higher up on the table. Remember I said top minus bottom? So what number's higher up on the table? The 0.51. Or the chlorine is higher on the table than nickel. Okay? So 0.51, 0.51 cathode minus the anode is going to be negative 1.11. And I get positive 1.62 volts for C. Everyone okay with that? Except for, what if the question didn't give you A and B? It just said, assume that the reference half cell has changed, the standard mercury 2 half cell. C. What would be the net cell potential of a standard chlorine nickel cell? And you're going, oh man, I gotta do all this work. I gotta do A, and then I gotta do B, and then I gotta do C. All for just one multiple choice question. Right? That's what you're thinking? No. Take your original numbers. From the data booklet, the original chlorine, which is the top number, is 1.36, and underneath that number is negative 0.26 for the chlorine and the nickel. I don't know if you can see that on the board anymore. Nope. For the chlorine and the nickel. Right? So chlorine, nickel, still can't see it. Just a minute. Maybe. Oh dear, now it's all going bad. Okay, so for the, oh dear, oh really dear. Okay, so for the chlorine and the nickel, we've got this voltage, subtract that voltage at the top minus the bottom, and I have positive 1.5, oh pardon me, 6, 2. The same as that.
You use the original or the new one?
Right, because it's the same 3 inches that I'm holding up on my ruler. It's just that the ruler shifted position, but the distance in that waterfall is still the same height. Okay? Okay, so ruler distances, don't love it, but my 2 sons are 3 years apart. And it used to fascinate, last year this was a big deal for them, that they would always be 3 years apart. And they would do the math. So they'd be like, so, because last year the one was 6, the other was 3, so they're 3 years apart. So when I'm 10, Carter will be 7. Yes. So when I'm 12, part of, like, he just didn't get that they will always be 3 years apart. Regardless of whatever age they are, the difference is still 3. Regardless of whatever number I set chlorine at, the difference between chlorine and nickel will always be 1.62, always. So regardless of what my standard cell will be, the height of that waterfall, the difference in those numbers will always be the same. So it doesn't matter what the scientists picked as the standard cell potential, because you never have a cell by itself, half a cell. It can't conduct electricity by itself. Zinc, zinc 2+, no spontaneous reaction, nothing to transfer the electrons to and from. Nothing will happen unless I put another half cell with it. Now I've got a full, complete story. I can have a transfer of electrons. Now I can have a voltage. So I'll always have 2 things. I'll always have a difference. And my sons will always be 3 years apart regardless of how young they were or regardless of how old they are. Regardless of what the standard cell is, these 2 will always be the same distance. So if you get a question that says, standard mercury, what would the net cell potential be? Who cares? You just take the 2 numbers and subtract them. Who cares what they picked as the standard half cell? Because the distance is always the same. Okay? All right. So, what if they asked you, because they haven't done this yet, but they will. So a little e here. What is the oxidation potential of a standard, let's go iron 2. Half cell. And still, if the standard reference cell is changed to mercury 2. So I'm still applying those 2 things. Okay? So what is the current iron 2 half cell reading? Negative 0.45. What did I just say? 4.5. Okay, so what is the oxidation potential of the standard iron 2 half cell? So this is what it is in your data booklet when the hydrogen is the reference. If we change it to my mercury, I need to then take this number and subtract 0.85 from it, just like we did before. And I find my new green number, which is 1.30. 5 and 8 is 13, right? Yeah. Everybody get how I got that number? Same as A, same as B, now I'm doing it for iron. Okay? Except for the difference between A and B is A and B ask for reduction potential. So I'm doing a GER. And this is asked for an oxidation potential. Therefore, I should be doing a Leo. Is that a Leo? No. So flipping that is the Leo. So flipping this then becomes iron goes to iron 2 plus 2 electrons. And if I flip the reaction, I need to flip the sign. So the oxidation potential ends up actually being positive 1.3 volts. Did you get that?
Yeah.
So if they ask you for the oxidation potential, you have to flip the sign because you're flipping the reaction.
Because all of these are in reduction.
Yeah. But the first thing you have to do is figure out what the voltage would be for the reduction. Because you're looking at a whole table of reduction, you're talking about reduction the whole time. So the first thing you have to do is the same thing you did for A and B. Then flip it. If you flip it too early, you get the wrong answer. Okay? That's it, you guys. All right? So, bit of an odd concept, and students tend to struggle with it, but it really is quite simple. It's not any more complicated than that. Connor?
Like instead of doing that, can you just subtract the negative, doing it the other way around it?
Can I subtract?
So like just take 0.85 and subtract negative 0.45, you get the same answer. Like instead of going the other way.
Can I take positive 0.45
Yeah.
and subtract 0.85? I won't get 1.3.
No, like you get 0.85 minus negative 0.45. And then which is just adding the term.
Yeah, it works out mathematically. Will you know which way to do it on your paper?
Well, that's what I was saying, because like, it's usually says top to bottom all the time.
Yeah?
Like, there you did negative 0.45 minus
Okay, why did I minus 0.85?
to get back to 0.
Yeah, to get the mercury to be 0.
Yeah.
So this isn't a cathode minus anode problem? I guess it kind of is, actually. It sort of is. I'm sort of asking what's the difference, what's the distance in that height between mercury and iron. Yeah, if that's the way you're seeing it, I think that would work out every time. If that's the way you're seeing it. Yeah. Okay. So what is the answer to part C? Why is the answer to part C the same as the answer taken from the standard hydrogen half cell? Because what's the answer to D?
On the scale.
What's an answer to D? Pardon?
It's just shifting up and down on the scale, so it'd be the same difference.
Right, the difference is always the same. The waterfall is always the same height. The distance between the two voltages will all be the same, whatever, right? Okay? Okay. Happy with that concept? Okay. It'll be on your next quiz to make sure that you got it.
Wait, what is the purpose of this though? Like how does this pertain to things? Like why would they ever shift the scale?
They wouldn't shift the scale. What it pertains to is that if a student understands this, they understand that these numbers individually by themselves are completely arbitrary. That actually don't have a battery until you have two half cells. And the voltage of that battery will always be the difference between the half cells. So therefore, a student truly understands what voltage is. It's the height of the waterfall between those two half cells,
That's why I don't get. Like why would they ever shift?
regardless of where the waterfall is falling from,
Okay, that makes more sense.
right?
So like it doesn't matter what your reference half cell is, it's just always going to be the difference, so you can always go
Right.
just top to bottom.
Right. If you have a 3-foot waterfall, okay, it doesn't matter if that waterfall is 1 meter above sea level, still a 3-foot waterfall. Or if that 3-foot waterfall is 3,000 meters above sea level, it's still a 3-foot waterfall. That's what they're talking about here. So the difference between those two half cells doesn't matter regardless of where your reference is, regardless of what two numbers are being subtracted. So mathematically, the math people love it. But actually what they're trying to do is theoretically, do you understand that voltage is a distance in those, the voltage of a whole cell is the distance between those two half cells. Not just some numbers plugged in your calculator. That's
I
why.
was wondering, I was like, why would they ever shift the
Yeah.
scale?
No. Yeah, that's why.
Okay.
And actually a lot of chemistry is based on this. Let's choose this as the arbitrary thing for whatever it is, like molar mass. They arbitrarily chose carbon-12 as 12. And therefore, if something weighs twice as much, we're going to call it 24. Oh, look, it's magnesium. And that's why magnesium has an atomic mass of 24, because it's twice as heavy as carbon-12. Not because it actually is 24. Okay? So that, a lot of chemistry is based on, let's pick this as a number for this thing, and then double it, half it, triple it, and everything else is based on that. Okay, so it's a good science concept as well. Right, for each of the following cells, write the cell notation. Remember how to do that? Electrode line, electrolyte, double line, electrolyte, double line, electrode. Label the electrodes. For this, they're looking for you to label, this one's the cathode, this one's the anode. Okay? And determine the cell potential. Well, that's cathode minus anode, top minus bottom. Okay, so just a little bit of practice. That'll take us to the bell, and then we are ready for electrolytic cells. Fingers crossed. Okay?